Okay, so here we're going to work an example to practice with reactors in series, and specifically we're going to look at CSTRs in series. So the example is the liquid phase reaction A goes to B is carried out isothermically and isobarically in a CSTR to 60% conversion. If a second CSTR is added downstream of the first CSTR, what should the volume of that CSTR be to achieve an overall conversion of 90%? And pure A is fed to the CSTR or to the first CSTR in both cases. So let's start by drawing out this problem. So we have a CSTR, pure A being fed, reaction inside, A goes to B, and we know that in this first CSTR, the conversion is 0.6. Coming out of this CSTR, we have A and B. Call this FA1, FB1. And we want to examine the case where we add a second CSTR. It's going to carry out the same reaction. It's going to have some conversion. We don't know exactly what that is, not yet. And coming out, we're going to have, again, A and B. We'll call that FA2 and FB2. So what we want is to design the system such that FA2 is equal to FA0 times 1 minus 0.9, or 0.1 times FA0. So in other words, we're looking for an overall conversion of A of 90%. So when we talk about overall conversion, we can look at, there's several different systems within this problem. There's the system of the first CSTR. This is one system. And so this has a conversion associated with the XA1. Or we can look at our second CSTR as a second system. That has a conversion associated with it, XA2. And then we can look at the overall system. And that is the conversion that we want to solve for, the overall conversion of A across the entire system. And so that's what this is the target value for FA2. So as a first step, let's look at our first CSTR because we have some information about that. I'm going to write down the mole balance for that. V1 is equal to FA0 XA1 divided by negative RA. I'm going to assume that RA is elementary. So I'll say assume so if I make that assumption, minus RA is equal to K times CA. I want to write this in terms of FA because that's the information I have. And actually I should say this is K times CA1. K times FA1 over the volumetric flow rate. This is a liquid phase reaction, so the volumetric flow rate is going to be constant over the entire system. So I can just write script V without any subscripts. So I can insert this back into my mole balance. Before I do that, though, I'm going to convert this flow rate term into a function of conversion. That's because I've written my mole balance in terms of conversion. So I want to write my rate in terms of conversions for consistency. So I'm going to say FA1 is equal to FA0 1 minus XA1. And I'm given this information, so I know that FA1 is equal to 0.4 FA0. So now I can substitute this expression into here, And then I can insert this expression into the mole balance. So that's what I'm going to do here. And I'm going to get V1 is equal to 0.6 FA naught times script V divided by K times 0.4 times FA naught. And if I simplify that, I get V1 is equal to 2 times the volumetric flow rate divided by 3 times K. Alternatively, I could write V1 times K divided by volumetric flow rate equals 2/3, but I'm going to leave my expression like this. So that's the first CSTR. Now let's look at the second CSTR. And I want to write my mole balance for that also, so that's going to look pretty much the same. V2 is equal to FA1 times XA2 divided by minus RA, where in this case minus RA is equal to K times CA2, which is equal to K times FA2 over the volumetric flow rate. FA2, we know, is going to be equal to 0.1 times FA naught. So I can insert this into here, and then I can insert this back into here. So let's do that. And I get V2 is equal to 0.4 times FA naught. That's what this term here is. Times XA2 times volumetric flow rate divided by K times 0.1 times FA naught. And I can simplify this further to get V2 is equal to 4 times XA2 times the volumetric flow rate divided by K. So now I need a value for this XA2, and I have all of the information to be able to solve for that. So based on the definition of conversion, XA2, which is the conversion within the second reactor, is going to be equal to FA1 minus FA2 divided by FA1. So the amount reacted in the second reactor divided by the amount fed. And I know all of those terms in terms of FA naught. And so I get that this is equal to 0.75. So I could insert this value into this equation. So that would mean that V2 is equal to 3 times volumetric flow rate over K. So that gives me an expression for the volume of the second reactor. If I want to know the volume of the second reactor that I need, I'm going to go back and relate that to the volume of the first reactor, which I also have an expression for. So I can say V2 divided by V1 is equal to 3 times the volumetric flow rate divided by the rate constant times 3 times the rate constant divided by 2 times the volumetric flow rate. So that would mean that V2 is equal to 1.5 times V1. So that is the volume of that second reactor that I would need in order to achieve a 90% overall conversion.